So I'd like to introduce Vladimir Koropin today to the colloquium for C2QA. Vladimir has a long and distinguished history in physics. He was a student of Ludwig Faddeev, and I was amused to see that he actually did his graduate thesis on the cancellation of ultraviolet divergences in one-loop gravity on the mass shell. After that, he has worked on many subjects, quantization of the Sine-Gordon model, quantum inverse scattering model, a lot of work on vertex models and statistical mechanical in StatMech, and correlation functions and exactly soluble models. What he's going to tell us about today is work on quantum search algorithms and the like. He's going to tell us about the hardware efficient search on NISQ computers, and can we reformulate the search to reduce the influence of noise. Vladimir, would you go ahead, please?
Okay, thank you very much for inviting me. It's a privilege. I'll start talking in a moment. I would prefer the following organization. The long questions should be postponed to the end, and the short questions like what's notation, I saw the typo, those can be asked in the middle of my lecture. So I'll talk about search. It's quantum search, Grover search. When I first tried to run it on Vigo, it works as bad as random pick because of the noise. So we decided to modify quantum search to adjust it to NISQ computer so it's less vulnerable to noise. So let me move to next. Of course, everybody knows Grover algorithm. Still, I want to remind to fix notation. So our database, it's structureless. Database is structureless, but there is one-way function. And also one target item in the whole database which we're supposed to find. So evaluation of the function is polynomially fast, and the inverse function is exponentially slow. That's a standard setup. The good everyday example of that one-way function is telephone directory. Okay, that's a function which will tell me like Oracle, query to the Oracle. If I guess correctly, then this function will give me 1. So I found it. Otherwise, for majority of the cases will be 0. It means like wrong guess. All right. So normal Grover starts in the usual standard way. I have all qubits set to 0. I apply Hadamard to each and every qubit. I get this like fully diagonal vector. So it is equal superposition of all basis vectors. Each and every basis vector in this, first of all, dimension of the Hilbert space coincide with number of items in the database, and each item in the database is become a basis vector in this Hilbert space. So I have I can use this one-way function to construct Oracle, Grover did. So query to the Oracle, also called in the literature phase kickback, is identical operator minus projection on that target item. People call target item solution or marked item. Different people use different notation in the literature. Anyway, that's only one item which the algorithm is supposed to find. And then there is a second, and of course this is query to the Oracle, is the reflection, the plane perpendicular to the Oracle. There is another reflection. It's called diffusion operator. I will call it from time to time reflection the average. This SN is average, which is totally diagonal elements, all the items weighted with the same weight. So it's normalized to 1. So diffusion operator will be realized through Toffoli gates. It's a reflection, the average, so projection on this S, which is total average of all items minus identical operator. Standard construction. So this is standard, but later we shall modify the diffusion operator. So our modification later will be the following. First of all, we change notation for this diffusion. We shall call it global. The normal diffusion operator, which Grover used, we'll call it global, because there will be another one, local. Actually, there will be several of them, local. So local is constructed like this. We shall separate the database into several blocks of equal size, and then introduce another diffusion operator where S will be replaced with the average from inside of the block, so smaller average. That will come. So far, this is normal, standard, usual Grover search. Okay, if I apply Grover operator, well, of course, Grover operator was application both Oracle and diffusion. If I apply this J times and measure, then the probability to find my target item is the sine square of this 2J, number of iteration plus 1, and theta is famous angle of law of Grover, sine theta is 1 divided by square root of n. So if J is about this pi squared of n divided by 4 integer part, then the probability close to 1. It's like 1 minus 1 divided by n. This is standard Grover again. So Grover algorithm is strictly optimal in terms of number of queries to the oracle. So in the oracular measure, this is the best ever. On the other hand, there are other measures of complexity. And the oracular measure is not specifically important for NISQ computer. I mean, the diffusion operator uses n-Toffoli gates, and then this is very expensive. If I write this in terms of C0, this will produce a lot of noise. So Oracle not only one operator. So the noisy things are gates, 2-qubit gates. We want to reduce the number of the gates. So I argue that depth of the circuit is better measure of complexity. And the Grover is not optimal in depth, so it can be optimized in depth. And that's what we're doing. So those are pictures of the quantum computers. This is to the left, we have a Sycamore. This is a famous Google computer. To the right, there is a Chinese, oops. To the right, there is a Chinese analog quantum computer. It's based out of quantum optics. There is laser beams. And then they named their quantum computer after ancient mathematical Chinese book, which is called 9 chapters. So these 9 chapters, right? 9 chapters of the mathematical art. Okay, so this is formal definition of the depth from, I don't know, formal definition of the depth, the longest path. So once again, our point of view that depth is more practical measure of complexity. And then we shall apply these ideas to some specific IBM Q computers, to the ones where I got permission to apply. And then we shall see that lower depth is better. So reducing the depth can reduce the noise. We'll see. Okay. So by now, our modification, we had this Grover diffusion, which was using the reflection, the total average of the whole database. Now the new diffusion. So we divide the database into this much block of the equal size, so, 2 raised to the power n small minus m small. So 2 to the m, this is number of items in one block. So the new diffusion operator is a reflection in the average C sub m, average inside of the block. So it's like smaller average, and this is different operator. So local Grover operator, the same query to the Oracle, it didn't change. And then this new local diffusion. So I mean, design in the following way that if I apply this local Grover to the empty block, the block with no target item, then nothing happened, it will be multiplied by 1. On the other hand, if I apply this local Grover to the block with where target item present, then something will happen. And by now, we have a 3, in the normal Grover, we have 2 kind of amplitudes, the amplitude of the target item, and also all other items has the same amplitude. Not so for this local. In this local, we shall have 3 different amplitudes. This will be target item. Then inside of the target block, there will be non-target items. And then there will be amplitude of the all other items within all other blocks. Okay, so local Grover operator. So by now we have 2 Grover. GN, this is global Grover, normal, usual Grover, and this new one, local. They can be represented as the elements of O3 group because of this 3-dimensional rotation. I mean, normal Grover can be represented as O2. This is O3. I'll show the picture in a moment. And this local and global, they don't commute between one another. This is O3, non-abelian algebra. So we'll talk about this more. So far, we have access only to small quantum computers. In the future, hopefully, we shall get access to the larger quantum computers and more complicated connectivity. Then we can use different over the course of the algorithm, we can use different local diffusion operators with different m's. This will increase, this will be O5 or something. So let's proceed. So this is the circuit. This is normal, usual Grover, global Grover in my language, query to the Oracle, and then negation Hadamard. This is just Toffoli gate, the representation of the, well, it's Control Z, but it still works. So this is global Grover, and this is local Grover. So I apply reflection only on one block in the database. That's a circuit, and that's the picture. This is normal standard Grover operator from the textbook can be represented as element of O2 rotation. The database has very high dimension. It's equal to the dimension equal to the number of items in the database. The dimension of the Hilbert space equal to the number of items in the database. But Grover iteration, the development is only in two-dimensional plane. So the two-dimensional plane, one of the bases is target item, the one which we want to find, and this is any other item. So all other items will have the same amplitude, and that's the other one. This is normal Grover, global Grover. In our local Grover, rotation is three-dimensional so far. We have a amplitude of the target item, then there is amplitude of the items in all other blocks, unwanted blocks, non-target blocks. And this is amplitude of unwanted items inside of the target block, non-target items in target block. So three-dimensional rotation. So element of O3. So in principle, when we shall get access to the larger quantum computer, we shall have a longer, G will be larger, the number of applications. Then we'll be able to use different local operators at the different stages of the algorithm. And then if I use diffusion operator of different size, this will increase the dimensionality of the sphere. So in the set of S2, it will become sphere of the larger dimension. So the group will be also O7, O5, or 7. I will talk about this a little bit later. So this was illustration. So the specific strategy which we apply was hybrid, classical and quantum search. So I will just show the results. We actually run this algorithm on some specific small quantum computer. So first of all, we initialize the state. So roughly speaking, the address of the target item is long sequence of bits. This is just the beginning, first, I don't know, 7 bits, and this is the rest. So, and this is give me separation of the database into blocks. So somehow we shall initialize database into some state of the first several items, and here this is just SN, total average of all items in one block. Then somehow we shall measure the first several items, and the correct sequence of bits will appear with some probability. So we'll just denote this for time being by this P. And then as for SM, here we can run the Grover. I mean, it's local Grover, but the idea is the same like Grover. So this is total average. And then we can apply these local Grover iterations on SM. So in the end, we measure. So after the measurement, the probability of success of finding the target item is the probability of the first step. Well, sometimes we shall just guess the sequence of bits for the first several bits. Well, it will be like 1 mainly in our example. Sometimes we'll be just guessing. And this is PJ. For in here, in this block, we run standard Grover, so probability of obtaining the rest of the address after J iteration, the same sign square of 2G plus 1, but the angle is different. So by now, the angle is local angle. It's B is number of items in the block, which is 2 to the M. So sine this of this new angle, 1 divided by square root of B. So by now we have two angles, right? We still from time to time will be using global Grover, which used the old angle where I had the N capital in here. And sometimes we shall be using local, so with another angle. So, I mean, in the future, we shall use several different local operations. It will introduce several different angles. Okay, so that's the idea. So depth optimization. So first of all, this is new search. New search by now, global standard Grover does not commute with local. So I mean, I should compose some word, some sequence of application, local, global. It will become a problem for the large quantum computers when we get access to those, because right now I have like one of this. So it's just a theoretical thing for the future. Right now, in these particular runs, which I will show, this didn't cause any problems. The success probability, I take this modified Grover. Here in the beginning, total average of the whole database. This is target items, square magnitude. That's a probability of success of finding this target item. Also depth, except of normal depth, we also introduce the expected depth. Expected depth, we just take the depth of the circuit of this and divide by probability of success. This probability very low, then we have to repeat the algorithm. So depth optimization, we want to just choose this sequence of all of this. A number of queries to the Oracle is equal to the sum of all of these J's. But right now, we're trying to downplay the oracular measure. So we want to minimize the depth. So we want to minimize the depth, changing these different J's, and also with respect to M. M is the size of the block. So when I subdivide database into several blocks, I have a choice of how many blocks. So that's the idea. So sometimes we measure in the middle of the algorithm, and then we call it different stages of calculation. The stage before the first measurement, we'll have sometimes one stage, sometimes two stage. Two stage means that we'll make a measurement in the middle. So, I mean, this is just notation. So this is one sequence of local and global, and then it has some success probability. And this is like first stage. Then we measure parts of the address, and then run another sequence of local and global reflection. So we have two stages. So the total depth is depth of the first stage plus depth of the second, divided by the product, both probabilities, probability of success of the first stage and the second stage. And the depth of optimization, we want to minimize this depth. Okay, so this strategy we can apply jointly, but it's clear to me that in the future we shall have many different quantum devices. Right now we do, but and they have different connectivity and other different technical characteristics. So the optimal search will be different for the different quantum devices. So will be different M, or during the course of the algorithm, we shall use several different local diffusions, and then this will depend on the device. Okay, so divide and conquer sometimes we apply. So this is just the list of the machine to which we get a permission, we get access. So we use Vigo, Athens, and Casablanca. Those are technical characteristics: readout arrow, quantum volume. So we tried those. We tried to run our modified search on these machines. Okay, so how we done this? We choose the toy oracle with a single qubit and with single qubit equivalent TOEFL gate. I mean, Control Z by n bits. We choose the target item randomly. So the target item was not always 0, 0, 0, but it was some sequence of zeros and one which we chosen. And then we run 30 trials and 8,000 shots every trial. So this is just a notation. The pictures will appear in a moment, but this is notation which you will see in the picture. So D3 M3 means that we used 3-qubit diffusion operator, and then 3 measurement, all 3 qubits was measured. This D2 M3 means that at first we use diffusion operator on 2 qubits and then measure all 3. This will appear G1 means random guess of 1 qubit, and then diffusion on 2 qubits and measurement 2. And here, this is 2 different stages. So at first stage, we make a diffusion on 2 qubits, then measure 1, and then after this will be for 4 qubits database. The whole database in this case will consist of 4 qubits, and then this D2 and this D2 run on the different qubits. Anyway, this is notation, so let's have a look. So in the pictures, you will see different characteristics. I will read them carefully. So there will be what will appear on the picture in different colors. Theoretical success probability, then experimental success probability. I mean, theoretically, I calculate from Grover, and then I run it on Vigo. I have a smaller success probability. Then the depth of the circuit also will appear in 2 installation: theoretical expected depth and the experimental expected depth. I mean, the computer tells us what's the expected depth. So let's have a look at the pictures. So here we run on, this is 2 qubits, I guess, no, 3 qubits. 3 qubits, the whole database is 3 qubits. And we run it with Vigo. So this diamond is theoretical calculation. And this thing with a circle, it's what came out of Vigo. So this D3, M3, this is standard normal Grover. Standard normal Grover with 2 iterations. In such a small database, I have to use only 2 iterations of Grover. So theoretical success probability is very, very good. What will come out is essentially worse. So it's like really, I mean, errors really destroy everything. So let's see how depths. So this D3, M3 in here. So the orange is the theoretical expected depth, but in Vigo, the expected depth was much, much larger. So that's the reason of such a dismal performance on the probability of success. Now, let's see. This looks better, right? I mean, theory and experiment are closer to one another. So here we did use our local operator. So with D2, local reflection on 2 qubits, 1 measurement, and local diffusion, I should have said. And this is local diffusion on 2, again, measurement of 2. So let's find this into here, D2 and 1. So the depth, I mean, the orange is theoretical depth, and the Vigo depth are closer to one another. Now let's have a look at the, I mean, this is not so bad. I mean, in here the theoretical expected depth and the experimental from Vigo kind of close to one another. So this is G1, the guess, we guessed 1 qubit, and then local diffusion on 2 qubits, measurement of 2 qubits. So let's find this, it's in here, G1, D2, M2. So success probability from Vigo not so bad. I mean, it's kind of close to theoretical. So what I'm trying to say that our strategy of I mean, partial search, we call it partial search when we so what we do, we separate database into separate block and run Grover on each block simultaneously, kind of renormalization of the size of the block. So this was 3 qubits. Let's have a look at 4. Oops. Let's have a look at 4 qubits. Okay, so 4 qubits. This is Vigo still. This is theoretical. This is what came out of Vigo. So probability. This is standard normal Grover. We call it global. So the theoretical probability is about 1/2. What came out of computer is 0.2, so not good approximation. So where is this? D4M4. So the depth, I mean, the theoretical depth, the orange is relatively small, and Vigo provide really large depth, and the performance is dismal. So let's have a look at the opposite limit. So this looks better, right? Theoretical and experimental close by. So what was the strategy in this case? So we ran local diffusion on 2 qubits, measurement of these 2 qubits, then another 2 qubits diffusion on the other 2 qubits, and the measurement. So it gives better correspondence between theoretical, better coincidence of theoretical and experimental. And in here, let's find it somewhere, D2M2, D2M2. So the depths also close. The orange is theoretical depth, and this is the depth of Athens. So it's better, it's better, it's better. So what I'm trying to say is that our strategy, our idea, work on the specific computers, quantum computers. So let's have a look. We tried for 5 qubits, but on this machine, 5 qubits is kind of, we need large machine. So 5 qubits, Grover search give really noisy results, meaning small probability of success. Nevertheless, our hybrid classical search give high probability. So let's have a look into here, circuits. So D5M5, this is standard normal Grover. So standard normal Grover probability of finding one target items, 26%. And then what came out of Casablanca is around 3%. So it's like much, much worse. On the other hand, if we run our hybrid, so we guess 3 qubits and then make local diffusion 2 qubits and measure 2, then the theoretical probability of success at 12.5%. But what came out of Casablanca is around 10%. So it's much better. It's much better. This hybrid works better, even on 5 qubits, of course. But to run it seriously, we need large access to large computers. And maybe we just go to the next transparency. Okay, so this is degrade ratio, degrade ratios. So R capital, this is a ratio, theoretical probability, which come out of my calculations, divided, I think it's the other way around. I think this is the typo. The ratio should be the real probability divided by theoretical. This is the typo. I apologize for the typo. So it's actually probability which came at the experimental divided by theoretical, not the other way around. So that's a typo. I apologize for this. So here I have number of 2 qubit gates, and here I have this ratio of real probability divided by theoretical probability. And then if I have a small amount of gates, let's say less than 25, then this ratio is not so bad, 80%. But after 25, there's a kind of phase transition. If I have more gates, then experimental ratio is much, much worse than theoretical. So here the noise killed everything. Everything's decomposed because of the noise. So it's not working. So this means that I should minimize number of 2 qubit gates in my runs of algorithms. Okay, this is like the picture which came out of our experimentalization. So actually, Rob, I'm coming close to the end. So you was worried about long lecture. It's short by now. So let's moral which I extract from all of this. So Grover algorithm was optimal if number of queries to the oracle, but not optimal in depth. So our strategy, we reformulate Grover in order to reduce the depth. I mean, we think that our modification is hardware efficient and make it less vulnerable to noise. The local diffusion operator can be used in the depth optimization, and when computers will become larger, there will be more kind of freedom, more possibilities for optimization. So let's read the last one. For the future computers, connectivity will be complicated, probably will have loops. I'm sure that will have loops. So we can modify Grover search using different sizes of the block at the different stages of algorithm. This will introduce different local diffusion operators, so different angles of this, Grover angle. And then the search will be high dimensional in the following sense. The Grover is rotation two-dimensional plane. The local partial search, which I explained, was three-dimensional rotation. But if I will have several local diffusions, then my rotation will be m+1 dimensional. So this diffusion Grover corresponding local and global Grover operation will belong to the group or m+1, where m will be number of the different diffusion operators. So what I'm trying to say that when the more complicated computers will come up, we'll have more power to adjust and to optimize search on the future computers. And we do expect that the optimal sequence of local and global and sequence of different local diffusion will depend on the hardware. They will be different for different computers to come. Okay, well, the outlook, there is a gap between theoretical computational complexity and the actual, computational resources. Yes, so that's what I already said. It's connectivity will produce different sequences of local and global also does not commute. Okay, so in the end, I want to thank my co-authors, Kun Zhang, Pujarao, Kwang Min Yu, he's from BNL, and Lim, she's also from Stony Brook University. And that's references. And actually, that's all I want to say. Thank you for your attention.
Thank you very much. Are there questions? I don't see any at first. Could you go back to slide 21?
Okay. So, I don't see the slide numbers. Wait. So,
keep going back. One more. Yeah, okay. No, you passed it. No, you passed it.
This?
No, forward.
This?
Yes, yeah. So why, it just right there.
Here?
No, you had it right there.
Here?
No, there. Just
okay.
leap 5-qubit search.
Yes.
So why I'm sure you explained this.
Yes.
Why is the theoretical probability of standard Grover it's so much higher than what you actually got, and your modified search was twice as worse, and yet it did. It's just, what, standard Grover is 25%, yes, and you only got 2%.
Yes.
And your modified theoretically should
modified to the low probability, right? My modified give theoretically half of that probability, but it's in the better agreement. So we just stopped algorithm before reaching high probability of success. So you asked me why I stop on this low probability for modification?
No, I'm just wondering how what theoretically should have worked half as good ended up working 3 times better.
You mean, right. Well, otherwise, it didn't, for 5 qubits, it didn't work well. So we have to rerun 5 qubits on the other ones. This was the best example to show the theoretical and experimental closer to one another. So I don't know, that's a better, we was minimizing this ratio of probability of the experiment and the theory. So I realize we'll work on this, okay, for the future.
I had a question, Vladimir.
Yeah.
I know you're an expert on quantum walk algorithms as well, done lazy quantum walk and things like that.
It's Mike McGuigan, right? Mike McGuigan, right?
Yes. I know you're an expert on quantum walks. I was wondering, is there any relation or simple relation you could explain between quantum walks and Grover search?
Right. This is a project for the future. Of course, in here, Grover, we reproduce database. I mean, theoretically, we look at the database as an unstructured database. So from the point of view of theory of Grover, inside of the database, there's no geometry, no topology. I don't know what's the distance between different items, and I don't even know which item is next to which. But sometimes database has a structure like two-dimensional lattice, so one-dimensional lattice, three-dimensional. So if my database represents the lattice, for example, then it has a structure. Then in classical case, the search, usually people use random walk. So, I mean, just walk around. In quantum case, quantum walk. Quantum walk, many people work on this, Ambanius, and there is a little bit of slowdown, except that the square root of n, there is also log. And this is our future project. I mean, we haven't done this. I mean, of course, if I have a square lattice, I can subdivide it into 4 squares and run local quantum search on each of the smaller squares. But this is still project for the future. We haven't done this. So good idea, but not done yet.
Okay, thanks a lot, Vladimir.
Okay, thank you.
Are there other questions? If I could ask another question, then you improve things by going from O2 to O3 or higher. Would you benefit by going to much higher? O10, O20, or will the noise kill you?
You know what, Rob, what I'm doing right now, I'm comparing theory with experiments, right? I mean, theoretically, I can do this. I don't see much advantage of hiring this OM. But on the other hand, I mean, theory means that I represent the database as a full graph where each and every element connected to other by a link, which will never happen. I mean, in the normal computer like a Vigo or Aston, this is the linear sequence, like one qubit, this is one in the line. So one of the future will be with 2 loops. So what I'm trying to say, the answer to your question will come when we shall try the theory with experiments. I think I hope, yes, but it will depend on specific connectivity and other technical characteristics of the future devices. I think it does, but this is like, theoreticians always happen that the theory will work for experiment on that level.
Okay. It was just a natural question to ask.
Okay, thank you for asking.
Are there other questions?
Okay.
No? Then let's thank Vladimir again.
Thank you.
And thank you, Vladimir. And with that, I'll close the session.